Your Tensegrity table wobbles like a toddler in a bouncy castle. And I'm going to show you how to fix that. First, we need to understand how a Tensegrity table works. Here I have a simple beam that's supported in a more intuitive way. The weight of the beam can be modeled as a force at the center of mass of the beam. The beam is supported at these two locations, and we can model those as upward forces. As the beam moves to one side, the weight of the beam is transferred away from this side and towards this side. When we get to the end, all of the weight of the beam is being supported on this side, and none is being supported on this side. It just barely balances. But if we go further, it falls over. So if we're going to suspend this center of gravity out past its support, we need a downward force on this side. So here we have a slightly less conventional way to support the beam. The weight of the beam is acting as a force at the center of mass out here. This is providing an upward force, and this hook is providing a downward force. As long as we maintain weight on this side of this beam, this will remain stable. If we let the weight move to this side of the beam, it falls apart. A Tensegrity table works the same way. The table's suspended mass is a force on this side, acting in the downward direction. In the center, this cable provides an upward force on the table, and on this side, these cables provide a downward force on the table. In fact, all Tensegrity tables work just like this, even the kind with 3 or 4 cables all around the table. A Tensegrity table with multiple lines around the center will always prefer one side over the other. If I put a mass on this side of the table, we're in the same situation we were before. We have a downward force at the center of gravity, we've got an upward force in the center, and we've got downward forces on this side. The lines on this side might as well not be there. They're not doing anything. They're completely loose. The same if I go to the other side. Force down, force up, force down, and these lines aren't doing anything. The only advantage this kind of table has is, well, they tend to not fall over if you build them right. Something to keep in mind is that as this distance gets smaller, or as this distance gets larger, the stresses on this member increase a lot. Here's an example of what that looks like. If you want to know how to calculate the forces on a system like this, I have some calculations at the end of the video. The next thing we need to understand is the mechanics of rope or chain or cable or 30-pound test braided fishing line. Rope is fantastic when it comes to supporting a tensile load. It's extremely structurally efficient. But it's a pile of hot garbage when it comes to shear or compressive loads. And this is what makes a Tensegrity structure seem impossible. It's natural human intuition that you can't push a rope. Here we have 2 masses supported on strings. This mass is supported with a single string, and just like all strings, the force is always in tension and directly aligned with the string itself. So if you put a side load on this, it begins to swing back and forth, and the direction of travel is always 90 degrees from the direction of force on the string. This means that the string can apply no forces to the object that would stop its direction of travel. This mass is supported by 2 strings at a slight angle. When you put a side load on it, one of the strings is always in a position to apply a load to the mass to stop that direction of travel. And this is the concept we're going to use to stabilize our tensegrity tables. Here's a close-up of the two tables I've built. These are both the same 3D printed model, but can be wired in different ways. This one, as you can see, is wired with single wires and all the stability that an upside down pendulum brings. And this one was wired with two splayed wires at each location, which nicely takes out the rocking back and forth. It's important to note that I angled the splay of the wires with respect to each other so it could take out motion in all directions. Here I have a diagram of a tensegrity table. One of the features of a table is that it's not moving or accelerating. And from that we can conclude that the sum of forces on the table equals 0. That is, if there was a force on the table pushing in that direction, there must be an opposing force pushing in that direction, so that when you add the forces together, you get 0 total force. This here represents the center of gravity of the tabletop and whatever's on the table. We'll represent that as an arrow right there. This force is being supported by a force down here on this center cable. Now, these two forces aren't aligned with each other, so that's going to cause the tabletop to want to twist in this direction. And that would put a torque on the table in that direction. Now, the tabletop isn't spinning in that direction, so just like sum of forces, we can say that sum of torques also equals 0. It's referred to as sum of moments. Moments in engineering speak is just another word for torque. So this torque must be answered by another torque, and it is. It's answered by a force at that location, which is causing a torque in that direction, and these torques balance out. So this is what we're going to use to calculate the forces on our cables. Now, to calculate a torque, we need two things. We need a force and we need a distance, because torque is simply force times the distance it is from the pivot point. Well, that means we need to select a pivot point. And for this, we're going to select this point right here. We'll call that point A. Now we can sum the torques around any point, and it'll always equal 0 as long as the object isn't moving. But this is a handy point to pick because a torque is a force times a distance, and this force is at 0 distance from that point. That means that force falls out. We can solve for one unknown force at a time. Our forces are this force, which is our known force. I'm going to call that 1, but it's whatever you estimate or measure as the weight of what you're putting on your table. And the units for this doesn't matter as long as you're consistent with how you use the units. So I'm gonna be doing these calculations unitless. We're solving for these two. I'll call this force X, and we'll call this force Y. We also need to label our torques either positive or negative so that the calculations make sense. So we're going to call a counterclockwise torque a negative torque, and a clockwise torque a negative torque, and a counterclockwise torque is a positive torque. So again, moments is just another word for torque in this case. We also need a distance. The distance between this force and that is always measured perpendicular to the line of force. It's not the distance between this point and that point. It's a distance measured perpendicular to this force. And that distance is 2, and the distance from this line here to the center is 1. So to start with summing our moments, we'll start summing around point A. Start with our force of 1, and then we multiply that by our distance of 2. And again, this is a negative torque, because it's trying to twist the table in that direction. So we'll add a negative sign there. And then we're going to add the torque from this force, which is x, times the distance of x from our pivot point, which is 1. And those torques sum to 0. If you solve for x, you get x equals 2. Now at this point, we could go to summing the forces. We have 2 forces in the downward direction, which add to 3. We have 1 force in the upward direction, so that force must be 3 to satisfy the sum of forces equals 0. But we can also continue with summing the torques. So we'll move our pivot point here. We'll call that point B, and then we'll sum from that location. Again, starting with this force here, we got force of 1. That's multiplied by the distance from the pivot point, which is 2 plus 1, or 3. And this again is a negative torque, a negative there. And then we'll add the torque from this force, which is y times its distance, 1, and that sums to 0. If you solve for y, you get y equals 3. That's how you calculate your forces.